Chapter 3 is all about numbers and proof. The first section that we're going to talk about is section 3.1, which is all about different types of mathematical proofs. So there are 4 different types of proofs we're going to go over, 4 in this section, 1 in the next. So the first one is direct proof, then we have indirect proof, proof by example, and proof by counterexample. And I'm going to go over what each of those mean in depth as we go through this section. So here's some refresher of mathematical shorthand. So this symbol right here means element of. ST stands for such that. This backwards E means there exists. So I could say there exists a element of a set Q such that A is even. I don't know. Or I could have used this symbol for the even integers, right? This is just some mathematical shorthand you're going to see as you're going through the book, and I didn't want you to get confused. R is the set of all real numbers. Remember, that's all rational and irrational numbers. Integers are all of the whole numbers and their additive inverses, so the negative numbers. Natural numbers start with 1. Even numbers are all numbers that are 2 times n, so 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, right? So that's all possible even numbers, and all possible odd numbers are 2n plus 1. And we're going to use these facts to prove a couple things, so keep that in mind. So definition 3.11 on page 94, right, says that if we have an integer a that doesn't equal 0 and it divides a bigger integer b, then there exists a k such that b equals ka. So if I have a is 6, for example, and b is 30, we would read a divides b, we could write it like this, because there exists a k of 5, because 30 equals 5 times 6, and 5 is an integer. Why don't we go ahead and make up a second example? So if I know that 4 divides 28, so let's let a equal 4 and b equal 28. I know that 28 is divisible by 4 because there exists a k. Well, what is 4 times what gives us 28? Well, that's 7. And 28 equals 7 times 4. And 7 is an integer. Next, let's talk about prime numbers. So a prime number is a natural number greater than 1 divisible by only 1 in itself, okay? Another definition is that a number is prime if it has exactly 2 divisors who are natural numbers. Note, this may be contradictory to what you've learned before. I believe I said this in college algebra. But 1 is not a prime number because it only has 1 divisor, 1, which is itself. So the first few prime numbers are, I don't know why I listed 19, 13 twice. What happened here? The first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and 37. Theorem 3.1.21 tells us there's no longer largest prime number, i.e. the set of prime numbers is infinite. And actually, it keeps taking longer and longer for these computers that are out there to find the next prime number, that if you find the next prime number, so you develop some strong computer that can calculate primes after primes after primes, if you find the next one, because it's so big, I have no idea how big it is, but if you find the next one, you win $1 million for finding a prime number. It's kind of crazy. So we've got a few propositions I want to go over. So if a is greater than 0, and if b is greater than c, then AB is greater than AC. So let's take a look at an example. So if I have that 7 is greater than 0, and negative 2 is greater than negative 3, then 7 times negative 2 is greater than 7 times negative 3. That's going to give me negative 14 is greater than negative 21. And this is a true statement. We could probably come up with another example. So let's say I have 2 is greater than 0 and 4 is greater than 6. Then 2 times 4 is going to be greater than 2 times 6. That gives me that 8 is greater than 12, so this is true. And it only works if a is greater than 0, right? Let's say a equaled 0. Well, then what would happen? If a equals 0, well, 0 isn't greater than 0, so we automatically fail, right? What if we had a was a negative number? Well, then we would have negative 1 is less than 0, which again wouldn't work. So a has to be positive. Let's take a look at proposition 3.14. If 0 is less than a is less than b, and 0 is less than c less than d, then AC has to be less than BD. So let's take a look at this example. 0 is less than 2 and less than 4, and 0 is less than 3, which is less than 7. So 2 times 4 is less than 3 times 7, so 8 is less than 21, which is a true statement here. Sorry about the typo. A direct proof is short and sweet. I like direct proof. I wish all things could be proven by direct proof. We assume our premises are true and use a logically valid argument. So let's prove that 3 divides 12, okay? And we're going to use our proposition 3.11 in order to prove this. So 3 divides 12, so let's let a equal 3 and b equal 12. Then there exists a k, and that k is 4, such that 3 times 4 equals 12, okay? We're using proposition 3.1, which tells us when an integer divides another integer, and that's how we could prove this statement.